Humans like to go far away, and they like to get there fast. This image is of a space shuttle, which is a reusable space vehicle. And when they re-enter, it generates an awful lot of heat. They angle the space shuttle up at this angle so that the base of it becomes a very large surface area, and they get a really large force and then a really large deceleration. But that whole area needs to be covered with ceramic tiles, which heat up very much. This video is going to go through vectors and the equations of motion. This is how we can calculate and predict how things are going to move. You're going to need to know the difference between vector quantities and scalar quantities. I'll give you an example first. Displacement is a vector quantity. And a similar quantity, a scalar version, is distance. This is a kind of classic example. If I were to go around a 400-meter running track, I'd have covered a distance of 400 meters. But my total displacement would be 0, because I'd be back where I started from. Now, this is a kind of definition for you. Scalar quantities have only size. Vector quantities have size and a direction. So, for example, speed is a scalar, and we'd say a speed of 5 meters per second is the size of your speed. You'd cover 5 meters per second, 5 meters every second. Velocity is the same type of quantity, but it is a vector. It means it's not just got the size 5 meters per second, but it's got a direction as well. And in this example I've given you, it's 5 meters per second north. And you'll just need to know really some other vectors are force. Force always has a direction. And acceleration. Acceleration can be positive or negative. Well, if it can be positive or negative, it's probably a vector. But here are some things that are always scalar quantities. Never can have direction. Mass. You can't have negative mass. Energy. You can't have negative energy. You've only got a certain amount of energy. And also time. We cannot go back in time. So therefore time is a scalar quantity. You may be asked to add vectors. It's called a vector sum. So here I have two vectors. I have 6 newtons, a force of 6 newtons from the left to the right, and 10 newtons, again, from the left to the right. Now, in one dimension, a vector sum is pretty easy. Here's my 6 newton vector, and I just need to add it to a 10 newton vector. It adds up to one vector with a size of this 16 newtons. Or it could be velocity vectors, and this time I have 10 meters per second from the left to the right and 4 meters per second from the right to the left. This time, when I add them up, I need to actually align them like this. So the total vector is the difference between them. It's this size from the left to the right, sum of 10 minus 4. The total vector is 6 meters per second from the left to the right. That's vectors in one dimension, but we could be asked to combine vectors in 2 dimensions. So here I have 6 meters per second downwards and 8 meters per second from the left to the right. Now I can work out the resultant vector of these two, the vector sum of these two, and also the direction that it is going. I can do this in 2 ways. I can do this either by scale drawing, in which case I draw an arrow to represent my 6 meters per second with a given scale. Let's say, for example, my given scale is 6 centimeters. And I can add to that the vector 8 meters per second as an arrow starting from the end of my other vector and going in its own direction. we always, when we do scale drawings, combine vectors top of the arrow to toe of the other arrow. Now, the resultant vector is from the starting position to the final position, this arrow here, which obviously you would draw with a ruler. And now if we were to measure that, we would have how many centimeters was representing the meters per second. Each centimeter represents 1 meters per second, and that would be the size of that vector there. And we'd have the direction of the vector as well. The other way we can do this, you may have noticed, that is a right angled triangle. So you can use any law you know about right angled triangles. Well, let's see. We know that a squared plus b squared equals c squared. That's Pythagoras' theorem. Let's have a look. A was 6, b was 8. So what is c? 6 squared plus 8 squared equals c squared. Reach for a calculator. 6 squared plus 8 squared equals 100. So c squared is 100. So c square root of 100 is 10. C is 10 meters per second. You could be given a vector and an angle and asked to work out what are the vertical components and what are the horizontal components of that vector. So it's kind of like working backwards. First of all, we're going to do the vertical component, and when you've got a vector and an angle, you're going to use trigonometry. This vertical component would be a vector here. Now, as you can see, it looks like a right angled triangle, so we can apply our trigonometry. First thing you do when you do trigonometry is write out SOHCAHTOA, so ka toa. That's our three relationships: sine relationship, cosine relationship, and tan relationship. Decide which one we're going to use. We're trying to calculate the opposite of the angle here. The vertical component of this vector is the opposite in the right angled triangle. So the one with the opposite and the hypotenuse, that's the diagonal one, is sine. So now write out the sine rule. Sine of an angle is equal to the opposite divided by the hypotenuse. Now input our numbers. Sine of 30 is equal to the opposite divided by 10. Rearrange. So I've got divide by 10 over here, becomes times by 10 over there. 10 sine 30 equals the opposite. That's what we want. Now we're ready to go to the calculator. In this calculator, you need to type 30 and then the sine button. Sine of 30 is 0.5 times by 10 equals 5. The vertical component of this vector is 5 newtons. Okay, next we're going to do the horizontal component of this vector. So similar kind of situation. The horizontal component would be this vector here. Again, it's just part of a right angled triangle. So again, we can apply our trigonometry. So ka toa. But now we're calculating the side of the triangle which is adjacent to the angle. So we're going to use our cosine rule, our cos. Cos of an angle is the adjacent over the hypotenuse. And now input our data. Cos of 30 is the adjacent over 10. rearrange once more. Got divide by 10, goes over here, whoops, not a very nice angle, to times by 10. 10 cos 30 equals the adjacent. Calculate that. Type in 30 on this calculator. That's the cosine of 30. Times that by 10 equals 8.7. 8.7 newtons is the horizontal component of that vector. Now we're on to the equations of motion, or these are sometimes called the Suvat equations, and they get their name from the algebraic letters that we give to the quantities that are involved in calculating motion. So S represents displacement, U represents initial velocity, V represents final velocity, A represents acceleration, and T represents time. These are the three equations of motion in algebra as you get given them on a formula sheet. V equals U plus AT. Final velocity is equal to initial velocity plus acceleration times time. The second equation of motion is V squared equals U squared plus 2AS. Final velocity squared plus initial velocity squared final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Then the last equation of motion is S equals UT plus a half AT squared. Displacement equals initial velocity times time plus a half times acceleration times time squared. You really need to know exactly what each letter represents and be confident using them, because you do not get told in the exam what they actually mean. You just get given the algebraic equations. So I'm going to give you some examples of the types of question you might be asked to apply the equations of motion to. I'll ask you to stop the video and have a go yourself, and at any point you can look back to the point in the video where we had the definitions of S, U, V, A and T, and the three equations that you can apply. First question then. A cheetah accelerates from stationary at 10 meters per second squared for 3 seconds. What's its speed at this point? So a little bit of advice. When you go through, think, what does this quantity mean? What does this quantity mean? Think, what do you have to calculate? Look for the equation, input the numbers and perform the calculation. Okay, pause the video and have a little go. So this 10 meters per second squared, that is an acceleration. So that's A. 3 seconds is T, time. And speed at this point is the final velocity. It's the speed at the end. So we're looking for something with A and T to allow us to calculate V. Now this question has a little bit of a tricky part in it, in that it says from stationary at the start, and that's a bit of data which isn't told to you explicitly, but you know the initial velocity must be 0 meters per second. So this is some other data that you need. So hopefully by looking through the equations of motion you can realise you need to calculate V, you've got U, and you've got A, and you've got T. So V equals U plus AT. U is 0, A is 10, time is 3, so I don't even need my calculator for that. 0 plus 10 times 3 is 30. At the end of its running, it's 30 meters per second. The cheetah runs at about 60 miles an hour. That's 30 meters per second. That's very, very quick. Next example then. Another question. Some students are measuring gravitational acceleration, so that's what you're trying to calculate. They drop balls from a height of 4.6 meters and time how long it takes to hit the ground. Their average time is 0.94 seconds. what's their calculated value of gravitational acceleration? So again, pause the video, think what quantities you've got, look for your equation and try and do the calculation. Okay, well, we're trying to work out we're trying to work out acceleration. So that's what we don't know. We've got 4.6 meters high. That's S, that's the displacement that the balls are travelling. And we've got T. This is the time it takes for them to drop. Now, again, there's some secret information. They drop balls, meaning that initially U is 0. So that's another little tricky part there. So you look through the equations and you find the equation S equals UT plus a half AT squared. Now, I think the easiest way, you actually want to calculate A, but I think the easiest way to work with this tricky bit of rearranging is to actually input the numbers. So S, 4.6 equals UT. Well, U is 0, T is 9.4 seconds, plus a half times by A. That's what I want to work out. So that's okay for that to be a letter there, an unknown, times 9.4 squared. Okay, well, let's do some rearranging and some simplification. 4.6, stay where it is. 0 times 0.94 actually just goes, that's 0. Plus a half times 0.94 squared. Well, I can do a half times 0.94 squared pretty easily. 0.94 squared is that, times by 0.5 means 0.4418A. Now I can rearrange because this part of my equation just disappears. I can rearrange for A. A equals 4.6 divided by 0.4418. That's my gravitational acceleration they'll calculate. 4.6 divided by 0.4418 equals 10.4. Not bad. And it's gravitational acceleration, so you need to put the unit on and correct unit, meters per second squared. Not bad considering gravitational acceleration is 9.81. And this type of question, by the way, would normally be coupled as well with a question about where that error might have come from. And the main error in this one is timing, and it's due to human error, human reaction time. Last example then. A car was travelling at 20 meters per second behind a slow lorry. The driver sees a sign indicating 225 yards before the end of the overtaking lane. He accelerates to 30 meters per second to overtake with a constant acceleration of 0.8 meters per second squared. Does he make the overtake before the lane runs out? And it tells you as well, 225 yards is approximately 250 meters. Again, pause the video. What information have you got? Select your equation. Have a go. Okay, well, what information have we got? We've got a car was travelling at 20 meters per second behind a slow lorry. That's an initial velocity. That's u. And he accelerates to 30 meters per second. That's a final velocity. That's v. And the other information we've got is a constant acceleration of 0.8, that's a. What do we need to work out? Does he make the overtake before the lane runs out? Well, does he make the overtake in less than 250 meters, basically? So we have to work out S. Does he actually make it in less than 250 meters? So again, pause the video, select an equation and have a go. This time we know V, we know U, we know A, but we don't know S. So we're going to use the equation V squared equals U squared plus 2AS. V is the final velocity, so 30 squared, equals U, that's the initial velocity, 20 squared, plus 2 times 0.8 times S, and S is the one we want to calculate. Rearrange and simplify then. 30 squared minus 20 squared equals 2 times 0.8, that's 1.6 S. So let's see what 30 squared minus 20 squared is. 30 squared, take away 20 squared is equal to 500. So 500 is 1.6 S. So S is 500 divided by 1.6, which is 312.5 meters. Oops. Meters. So no, he doesn't. He is 62.5 meters further than the end of the lane. Overtake safely, guys. Now, if you like that video, then go ahead and like that. If you want to see more and you want to know when they're coming up, then subscribe. Press the subscribe button now, and please do tell your friends if you think they could also use from a bit of Mr. Betts Physics.